Hi everyone. Sorry I can't be here today, but hopefully this video recording will sort of help you through the notes today and give you some time to work on worksheets. Take a look at this. We left off on this slide here, talking again, just a quick reminder that the total area underneath a velocity versus time graph will give you the displacement, delta x. And we use that idea, and we could actually break this into two parts here and find the area of the triangle and the rectangle to figure out what the total displacement was. And the area of the rectangle, just the initial velocity, which would be this point right here, times the time elapsed, and I'll just call that t. And this is the final velocity up here. And again, remember, this can be called either v initial or v naught, depending on which class you happen to be in. The area of the triangle, 1/2 base, which in this case is delta t, times the height, which is the change in these two, v final minus v initial. And you can rewrite that equation as down below here, just the sum of those two, area of the rectangle plus the area of the triangle. Or if you rearrange that a little bit, you can rewrite it this way. But let me show you real quick where that comes from. If you take a look at that last equation again, just the area of the rectangle, area of that, you can go ahead and distribute the 1/2 t through both of these last two pieces here. So here's the 1/2 t. But you'll notice now that this term right here and this term right here are the same. We just have v0t and then negative 1/2 v0t. Combine those together gives us just positive 1/2 v0t plus 1/2 v final t. If we factor out the 1/2 and the t, we can actually write it this way. And you might say, hey, how come we didn't put the 1/2 in front of that? Well, there's actually some reason behind that. If you look real quickly at this term right here, what is that? Well, this term right here is actually the average velocity. The initial velocity plus the final velocity divided by 2. It's the average of those two values. And so if you go an average velocity, or if you take your average velocity times your time, it'll tell you how far you travel, your delta x, your displacement. And so it makes it pretty easy. And now this one, you're like, okay, got this. So the area underneath the velocity versus time graph gives you displacement. That's what we just used in the last couple of slides. What's the displacement in this case between 0 and 4 seconds? You're like, oh my goodness, it's the area underneath this graph. How do you solve this one? AP's never asked this one, but if you had to, what you could literally do is count squares. And yes, you'd have to approximate half squares down here too. And you could count them all up all the way along here and eventually come up with, this one's a little painful, you'd have to like 2/3 of a square. You could add them all up and estimate. It wouldn't be exact, but it'd be close. Brain break. From each word below, remove one letter and rearrange the remaining letters to form something you might have for breakfast. So at this point, you might want to pause the video, but let me first do one for you. The only one I recognize is this one. If you drop the C and rearrange the other ones, this becomes bacon. So if you want, and I do actually encourage this, it actually gives your brain a break from all the math. See if you can do the other 5 of these. Again, pause the video now before I give away the answers. Welcome back. See if you got any of these. Butter, tribute butter, telecom omelet, gamble bagel, cleaner becomes cereal, and meatloaf becomes oatmeal. What letter did you have to drop there? Anyway, a tricky one, but still kind of fun. All right. So real quick here, remember acceleration is defined as the change in the velocity over change in time. It is a vector quantity. It does have a direction. It can be positive or negative. There is no scalar equivalent to acceleration. There was a scalar equivalent to displacement, that's distance. There's a scalar equivalent to velocity, that's speed, but there is no scalar equivalent to acceleration. And if you have a graph then of velocity versus time, you can actually go ahead and find the slope of that graph at one point by drawing a tangent line. The slope of that line, by definition, is the change in rise over run, which in this case would be the change in the vertical axis, change in velocity, over the change in the horizontal, which many of you would recognize. Oh, wait a second. That's the acceleration. And you're absolutely right. So the slope of the graph at each point here would tell you the acceleration at that point. So at the top here, at that brief instant, the velocity is not changing for that brief instant. And the acceleration at that instant is literally 0. And then over here, the acceleration would be negative. And you're like, okay, got that. So you could find at each point. Real quick, try this one. If you had to sort of figure this one out, given this position versus time graph, what's the velocity? And the answer is, oh, wait, the slope of the position versus time graph gives us velocity. Oh, yeah, the slope is becoming more and more positive, which means our velocity has to be getting more and more positive as well. So something like this. Once you have that, how do you find acceleration? Acceleration is the slope of this graph at each point, which in this case seems to be constant and positive, and so you would draw this graph. Pretend that's a straight line. In general, you could actually figure out this. I actually drew a better line there than I did there. The slope of the position versus time gives you the velocity at each instant, so you can then graph that. The slope of the velocity versus time graph gives you the acceleration at each instant. And the one new thing on this one is the area underneath this graph actually tells you delta V, your change in displacement. And you already knew that the area underneath the velocity versus time would actually give you the displacement. We've done that before already. So here it is, real quick in general terms. You can sort of visualize what's happening. Slope of this gives you that, slope of this gives you that. The area underneath this one gives you delta V. Warning on this one, these are the change in the position, the change in the velocity. They don't give you the absolute velocity. What do I mean? Say, for example, the area underneath this one was 40 meters per second, just making up some numbers. Does that mean at the end of this time that the object's going 40? Well, it would if it starts out at 0. But if it started out at 10, it would actually be at 50 meters per second by the time we were done. It just gives you the change in the velocity, not the actual velocity. Real quick on these two, or on this one, there's a quick compare one. Rank the magnitude of the change in velocity during each of these time intervals. Don't forget velocity is a vector quantity. Delta V would be equal to the final minus the initial. So in this case, what's the change? It gains 10. It would be the final velocity, 20 meters per second, minus the initial 10, and so you get 10 meters per second if you plug it in that one. This one, magnitude is negative 10. I'm going to leave out the meters per second. This next one down below here, rank C, goes from positive 10 to negative 10. And then this one goes from 30 to 20. So this would be negative 10 meters per second. C, the final is negative minus the initial, which is positive. This one's negative 20 meters per second. And since we're only ranking the magnitudes, not the actual bits on this one, the answer on this one, C is the greatest, followed by A equals B equals D, which are all the same. All right, worksheet 5. If you have it, you can take a quick look at this one. I want to spend a little time with this one because it is a little challenging. What you're doing here is, given a position versus time graph, trying to figure out a few things on this one. So what would this one look like? Oops, I should have actually gone negative as well. Oh, shoot. Forgive me for a second. I'm going to quick choose eraser and see if I can, I'm going to clean up this line just a little bit. Apologies there. Not happy with my graph. Why? Because I know I'm going to have to go negative at some point here. So here's my velocity versus time graph. What's it going to look like? Well, for the first couple seconds, looks like I have some positive velocity to about here. Then it goes 0 for a while. I'm going to make it thicker here so it's easier to see. And then it goes very large negative for the next part. Written description, um, I'm going to say it verbally because it's just too hard to write on this one. The object moves away from the origin in the positive direction at a constant rate, then stops for a while, then moves back towards the origin at a more rapid rate. What would my motion map look like? It would start at the origin, move away at a fairly constant rate. I'm going to draw it like this. Then it's going to stop for a while, so I'll stack. And then it's going to move back at a more rapid rate. I'm going to draw that just by going like 3 across here. And again, typically we put little velocity vectors on here just to make it easier to see what in the world is happening. Oops, that's supposed to be an arrow. I'll fix that. And this one here, and then back at a more rapid rate. And I'll do just one more with you on this one. So down here in the next one, we have a velocity versus time, and we have to figure out position versus time. It starts out with a very large negative velocity. And it doesn't matter where you start these, but in this case, what's going to happen? This negative part means I'm going to move away from the origin, gaining displacement in the negative direction, something like that. And then during this next part, I have a positive velocity, but it's not quite as steep. So I start heading back towards the origin, and then I stop, which means my position stays constant. And so this should have a smaller magnitude of slope than this one. I don't know if it does, and that should be a straight line. But the graph should look something like that. Describing this thing, what's going on, it's moving towards or it has a negative velocity, means if it's in the positive, or let me draw from my graph. If it's starting from the origin, it's moving in the negative direction at a constant rate. Then it moves in the positive direction towards the right at a slower constant rate, and then it remains stationary. Motion map, I'm going to cheat. I'm going to make this my 0 point just to make it easier. So in this case, moving backwards, I'm going to go 2 units here for each spot. This is the part where it's moving constant. And then it immediately starts moving backwards at a slower rate. You know what? I'm going to do this just to make it easier. So I'm going to do like an empty dot here just so you can sort of see where it would have been. And now it starts moving backwards. I'm going to stack that at a smaller rate. So I'm going to do 4 dots here. And then it stays stationary, and those will just stack. So my velocity, adding the little velocity arrows on this one, backwards, 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 and then forwards again, but at a slower rate, and then constant for a while. All right, you can sort of figure out how these work. I'm going to go next page here and just do one of these that actually has, I think, 2 objects moving. Yeah, those aren't going to be too bad. Yeah, take a look at this one. Object A starts 10 meters to the right of the origin, which would be in the positive part, and moves to the left at that. Object starts at the origin and moves to the right. So what would my position versus time graph look like for this thing? Something like this, and I'm going to color code these. So this is position versus time. I should have labeled the other graphs as well. So what do we have here? I'm going to go with, I need some colors. Purple for object A. Starts 10 meters to the right of the origin. That'd be in the positive direction, and moves to the left at 2 meters per second. So it's going to do something like this with a constant positive slope as best as I can draw it. Object B, on the other hand, starts at the origin and moves to the right at 3 meters per second. What's that going to do? It's going to start out at 0. I guess I should have labeled that one. And it's going to go upward, but at a greater slope. And yeah, logically, they should cross at some point. This should remind you of worksheet 1, where you had the 2 bicyclists way back when. Yeah, it's very, very similar. Velocity versus time graphs, what's that going to look like? In this case, I'm going to draw it since I'm already in the color mode already. A is going to have a smaller velocity, and B is going to have a greater velocity. And I'll draw the axes in here in just a second. Both positive. Doesn't matter where they start, it's just the slope of their lines. And so in this case, the velocity versus time graph should look something like this. And these are supposed to be qualitative graphs. They're not meant to be, oh my goodness, time and velocity. Please excuse it. This should be time, and this should be x over here. I actually switched the axes, so I'm so sorry. Sorry, just noticed that now. Motion map, how in the world do you draw this one? This one gets a little bit more exciting. Usually what we do is we draw one above and one below. So this is position X. And so B is easy. I'm going to do that one first. B starts at the origin and moves at 3 meters per second. So I'm going to draw those dots kind of further apart. And then A starts ahead of the origin. I'm going to put it about here, and it's moving slower. So I'm putting those dots proportionally closer together. And then adding velocity vectors to those real quick, just so you can sort of visualize it. Yeah, B is moving faster than A is. And this one's slower. And yes, I should label those as well. I hate switching colors back and forth, so forgive me. I'm just going to write this one as B, and this is A. And you should be able to figure out this one. What's happening here? A starts at the origin, B starts further out, but they're moving at the same velocity. And you should be able to graph those pretty easily. All right. A little quick note on these. So let's spend a little time with acceleration. Remember what this literally means. It literally means when you write 4 meters per second squared, the second squared confuses a lot of students. It really just means in this case, you're gaining 4 meters per second every second that you're traveling. So starts from rest, which means its initial velocity is 0. It means our graph is going to look something like this, and it's gaining 4 meters per second. So after 1 second, it should be going 4 meters per second, 2 seconds, 8 meters per second, 3 seconds, 12 meters per second. What would it be going after 10? The answer is, oh, okay, it's gaining 4 meters per second every second for 10 seconds. Should be going 40 meters per second. Hopefully you got that one. This time, it's starting out already with an initial velocity, same acceleration. So our graph is going to look something like this. It's again accelerating the same rate. This time, what's its velocity at 1 second? Well, it started out at 10, gains 4 meters per second. It's going 14. After 2 seconds, 18. After 3 seconds, 22. And after 10 seconds, it'll gain 40. It was already going 10. Should be at 50 meters per second. Oh, shoot. I actually have graphs on here already. Oh, I've got answers on there too. All right. No worries. And so you've got the answers. All right, take a look at this one then. Car is moving at 10 meters per second and accelerates at a negative rate. What does that mean? It means that it's going to be losing that amount every single second. So our graph is going to look something like this. What's its velocity going to be at 1 second? Well, it starts out at 10, loses 2. It's going to be at 8. At 2 seconds, it's going to be at 6, losing another 2. 4 seconds, or at 3 seconds, it's going to be down to 4. And at 20, it's going to lose 20 meters per second. It was going 10. It means it's going to be going negative 10. It's losing 20 from where it started. One more, in this case, a negative velocity with a positive acceleration of 2 meters per second every second. After 1 second, what it would be going? It would gain 2. It would be at negative 8. It would be at negative 6. After 3 seconds, it would have gained 6 meters per second. It'd still be going negative 4. And after 20 seconds, it would gain, after 10 seconds, it would gain 20 meters per second, which would put it at positive 10. Hopefully you're pretty confident with this at this point. What we were doing logically there was really this. Remember, delta v can be written as the final velocity minus the initial velocity, so this term right here. And if you take that equation, a equals this over delta t, if you rearrange it, just slightly multiply both sides by delta t and then move v final to the other side, you get this equation. And this equation is our next big one. And it's actually the one we were using on the previous slides without realizing it. We took the initial velocity plus the acceleration times time to get us our final velocity. So real quick plug and chug one here. With a little bit not as nice numbers, if the acceleration is negative 4.3 meters per second squared, how long will it take this car, which starts out with this initial velocity, to stop? If you just plug it in and solve it, you'll discover, just about 7 seconds. All right, a little bit of mathematics real quick on this one. Just a real quick, if we use that previous equation, the one we just used here, acceleration is this over that. Multiplying both sides by time, we get AT is equal to this minus this. Well, if you remember on the previous slide when we did this, we had this equation right here before we got to our final one. Notice it also has this VF minus V0, or V naught, which means we can substitute AT in there for that. And if you do that, you end up with this equation right here. Delta x is equal to v0t plus 1/2 at squared, and that's usually enough. But again, remember delta x is equal to v or x final minus x initial. And so you can also rewrite it this way. And this is our third big equation. This one describes the position of an object at any given time, given the initial position, initial velocity, and its acceleration. Again, all of these equations only work for constant accelerations. They don't work for anything else. Your last worksheet tonight is dealing with accelerated motion, a ball rolling down a ramp. Do not get confused on this. The vertical position up and down doesn't matter at all in this case. It's only one-dimensional motion along this axis, this way. Ignore the up and down part. What's the up and down part? It's just giving our ball, which is right here, something to accelerate down. So in this case, our ball is going to be accelerating down this ramp and gaining speed at a regular rate. I always recommend on this graph to always start with a velocity versus time graph. In this case, the initial velocity is 0. And what's going to happen here? It's going to gain velocity in the positive direction at a regular rate. So this graph is going to look something like this. The acceleration graph, remember, is just the slope of this graph at every single point. And if you check, sure enough, the slope is constant positive, which means our acceleration is just a constant positive value. Position versus time, some of you are like, oh, of course, duh, Ms. Clommer, if it's doing this, it means the slope of this graph has to be increasing with time, which means this graph has to look something like this, kind of exponential. Motion map, that's going to be pretty straightforward. Let me just erase my little bar part here so you can sort of see it. And to do the position versus time graph, we actually assumed, or I started at 0. Why? Because this was at 0. Motion map, up here on top, you could either draw the motion map here or down below over here. I'm just going to draw it here. What's happening? The object is moving at is gaining velocity as it goes down the ramp, something like this, and it starts out at 0. And this can be qualitative. I probably should add one more point in here, honestly, to make that, yeah, that's better. And so what's happening here? It's gaining velocity, small at first, then getting bigger and bigger and bigger as it goes down. I can't draw the last one. It would go off the edge of the page, so forgive me. And then the part that always drives students crazy. This part here, E. Write a general mathematical expression of the relationship between x and t. And a lot of students go, whoa, wait a second. How in the world am I supposed to do that? Well, in general, remember that the final position of any accelerating object is just given by this equation. The initial position plus v sub 0 times t plus 1/2 at squared, the one we derived on just the previous slide. So in this particular case, it actually becomes very, very simple. Why? The initial position is 0. The initial velocity is also 0. So these two terms drop out. So what's the general equation then for this thing? The final position at any given time is just going to be 1/2 at squared. We don't know the acceleration, we just know it must be constant. And that's all you would write for this one. What about the velocity equation? Our general equation for velocity, if you remember, is final velocity is equal to initial velocity plus a times t. And again, in this case, the initial velocity is 0. I'll draw a an arrow here. So what's our equation for this one? The final velocity at any given time on this one is just equal to a times t. And it gives us this line right here. Finally, what do we write for the acceleration? The acceleration is just some constant number. We don't know what it is, but you can just write it's a constant. Some people are like, should I write positive constant? You could, but any constant could be positive or negative. It's just a constant value. And that's what this first one would look like. You're like, oh, okay, Ms. Clemmer, that's not so bad. Yeah, let's try another one real quick. Oh, actually, I put it on here. Okay, gosh, I did all the work. Never mind, we'll skip through that real quick. You already can see it. What about this one? Well, this one, what's changed on it? The initial position here is no longer 0. It starts out, if you look at the number line here, at about 10 meters. What does that do to our graphs? Our position versus time graph is going to start out now at 10. What does that do to our velocity graph? Well, our initial velocity is still 0, and it's still going to accelerate at a constant rate. So the graph here doesn't change at all for this, nor will it change for the acceleration, which is the slope of this thing. The acceleration is still constant positive. How does it change the position graph? Well, the position graph is going to look very similar to what we had, except now it's starting out at 10. So it's going to start out flat and gain slope at every single point. Pretend that's exponential and look something like that. Motion map, everything looks the same except it's going to be shifted over a little bit. So this is our number line, or our position versus time graph for this thing. This is x. The first dot's going to be at 10 meters. And then it's going to gain speed from there. I'm putting them a little bit closer this time so I can draw maybe some more arrows on this one. Sorry, it takes me longer to draw than it's worth. And then you're going to write the equations, and I probably put them on here, so this time I'm going to use that one. So starting out with the general equation, in this particular case, the initial position here is not 0, although the initial velocity is. So what does our equation become? It becomes 10, missing that, plus 0, 1/2 at squared, or you could just write it that way. For velocity, it stays the same. So that just becomes that. And down here, you can just write accelerations constant. All right. This one, I want to just take a quick look at it. This one is completely interesting. The ball starts out here at 50, and then it's going to roll back and forth. I would suggest with the velocity one, initial velocity is 0. What's this thing going to do? It's actually going to, first of all, gain velocity. It's going to start rolling this way and gaining speed in the negative direction. Starts out at 0. It's going to gain it in the negative direction. And then it's going to roll across this flat part right here at a constant rate. We assume no friction in this particular problem. So it does that. And then it's going to start rolling up this part. And during that part, it's going to lose velocity. So it's going to do something like that until it gets to the top here where it's going to stop briefly again before it starts rolling downward. As it's rolling downward, it's going to gain velocity in the positive direction. Then it's going to roll across this flat part where it's going to be 0 again. And then it's going to go back up to where it started, back to right here again, and before it repeats it again. My acceleration graph gets really exciting real quick. I've got negative here, 0 here, positive here, all the way across here, back to 0, and then negative. And yeah, I could do little dotted lines. Sorry for my fact that these should be completely horizontal. They're not quite. But you get something like that. And then finally, position versus time. This one just gets bizarre. It starts out at 50, so I'm going to start up here. It's going to gain slope in the negative direction while it's accelerating, then move at a constant rate, and then that's during this part, and then it's going to lose velocity till it hits 0, and then it's going to gain velocity, and then till it gets about here, and then it's going to go straight again during this flat part here, and then it's going to lose velocity here. It's going to look something like that. Motion map on this one gets real exciting real fast. It starts over here at 50, and what's it going to do? It's going to oscillate back and forth, and I would literally so it's going to gain velocity in the negative direction, then move at a constant rate for a while, then start slowing down so these dots get closer together again. And then it's going to repeat, and I'm just going to stack those up on top, and the positioning on those should be about the same. And I'll draw my little velocity vectors on these in just a second. But yeah, it's kind of an interesting problem. And I know I should have moved that last one up, but I want to make sure this video doesn't take forever. Here's my constant, then slowing down, coming to a stop, and then up here it starts moving backwards. Yes, that dot should be up here, then gaining speed, then gaining speed, and gaining speed. Hopefully you can work together on this worksheet and solve a bunch of them. We did a bunch of them together. This was number 8, but I left a few of them for you to do. Oh, I actually do have, okay, segments in here. Did I actually draw a bunch of this in? Okay, never mind. With that, I think I did actually draw it all in. Oh, wait. Could you please I just want to make sure, whoops. Nah, I gave away the answers. These are velocity versus time graphs for toy robots. Rank the displacements. So remember, the displacement's going to be the area underneath the graph. In this case, that's 1, 2, 3, 4, 5 units. In this case, it starts out about half. 5, 1.5 times 5, 7.5, 3.75 if you divide it by 2. This one, a little bit more than that. I won't do the math on this one yet. This one looks like 1.5 times 5, so 7.5. This one, there's much positive as there is negative. The displacement on this one, 0. And then this one looks like it goes exactly 1, so 2.5. The only tricky one on this one, so ranking these, this is largest, that's smallest. This one, because it goes a little bit further than this one, has to be just a little bit bigger than 3.75. I won't actually do the numbers on that one. So ranking these, biggest, so D, A, C, B, F, E. I hope I put that in the right order. Yeah, so it's kind of fun, just good practice with that one. And then take a look at this. So with a single velocity versus time graph now, you can actually calculate all of these. What's the object's initial velocity? Answer is 40. What's the object's acceleration? Well, it loses 40 meters per second in 4 seconds, so negative 10. And the object's displacement, you can either use the mathematical equation or you can figure out the area underneath this, which we did before, 80 meters. If I put answers on this one, I did. And so pretty straightforward. This one. what direction is she moving, and what direction is she accelerating? So remember, acceleration is a vector quantity. How do you solve it? So in this case, she is moving this way. Her acceleration is in the same direction. She's gaining velocity towards the right. In this case, she's moving towards the right, but is she gaining or losing speed? She's losing it, which means the acceleration must be acting against that velocity vector. And then this one, she's moving towards the left in the negative direction, and she's gaining velocity towards the left, which means her acceleration also must be pointing that way. And then finally, this one, she's heading to the left. That means her velocity is pointing to the left, but she's losing that velocity. The acceleration must be acting against that velocity. It must be acting this way. All right. At this point, I'm going to stop because we've talked too long. Hopefully you feel pretty confident and can solve this. We'll see you again next time.